Welcome to this chapter on Gauss's Law, a foundational concept in electromagnetism. In this chapter, we will explore how electric fields interact with surfaces, how symmetry helps us simplify complex problems, and how conductors behave under electrostatic conditions. First, let's begin by understanding the concept of flux. Flux is a general term that describes the amount of any vector field passing through a given surface. Imagine wind blowing through a window. The amount of air passing through is the flux. In mathematical terms, flux is the dot product of the field vector and the area vector. Again, flux is the dot product of the field vector and the area vector, which means it considers both the magnitude of the field and the angle of incidence. So if you look at this mathematical expression, you see phi sub E is E dot A, is EA cosine theta. Obviously, the dot product involves the cosine of the angle between the field vector and the area vector. So here's an example. An electric field passes through a loop of area at an angle. Find the electric flux. So the angle is given as 60 degrees, but that's not shown there. And so as you can see, phi is E dot A, which is EA cosine theta. When you do the math, you get 0.0075. And the unit of electric flux must be Newton per coulomb times meter square. Okay, Newton per coulomb times meter square. So this is out because Newton per coulomb is the unit of electric field and meter squared is the unit of area. So that is specific to electric flux. So what is electric flux? Electric flux is a specification of this idea of flux. And here we focus on electric fields. Electric flux tells us how much electric field penetrates a surface or passes through a surface. If the field is perpendicular to the surface, flux is maximized. If the field is parallel to the surface, flux is zero. For closed surfaces, the electric flux measures the net number of electric field lines entering and exiting. So you have to consider both. Now, we've already seen that to calculate electric flux, we use the formula, the electric field multiplied by the area and the cosine of the angle between them. That's for regular surfaces, but for irregular surfaces, or maybe where the fields are changing or varying, we integrate over the surface. So generally, electric flux is close the surface integral E dot dA. Now that is diagrammatic. That is represented by the diagram given below. So in this question, an electric field, 100 Newton per coulomb, is oriented at 45 degrees to a square sheet of area 2 meters squared. Find the electric flux. E times A times cosine of 45 gives 141.4 Newton meter square per coulomb. Here's a second one. A hemispherical dome of radius 1 meter sits in a uniform electric field of 50 Newton per coulomb. kind of shown by this diagram, find the total electric flux. Now, in this case, the area is 2 pi r squared, and that's because the surface area of a sphere is 4 pi r squared. If it's a sphere, it's 4 pi r squared. Now, this being a hemisphere, that's divided by 2. That's why it's 2 pi r squared. And then you have the electric flux is E times A, because in this case, you have to note that theta is 0 degrees. Theta is 0 degrees because the angle is taken with respect to the perpendicular drawn to the surface. This is very important. So when you take the angle, you take it with the perpendicular drawn to the surface. And since the field is along that perpendicular, that's why the angle is 0. So if you have a surface like this, for example, and the field is passing perpendicular to it, okay? Once again, the angle would be 0, not 90, because the area vector, its direction is given by the perpendicular drawn to the area. This is one part where students make mistakes, so be careful on that. Again, the area vector is in a direction given by a perpendicular drawn to the surface. So now let's go to Gauss's law. Now, Gauss's law is a powerful statement about the relationship between electric flux and the enclosed charge. It relates the electric flux with the charge inside a surface. It tells us that the net electric flux through a closed surface is proportional to the charge enclosed within that surface. That means the more the charge within a surface, the greater the electric flux passing through that closed surface. Mathematically, the total flux equals the enclosed charge divided by the permittivity of free space. We can see that here. So on the left-hand side, we have the electric flux. On the right side, according to Gauss law, this electric flux is equal to the charge inside divided by the permittivity of free space, which we know, epsilon naught, we know that it's 8.85 times 10 to the negative 12. Okay, so that's the value of epsilon naught. Now, what is important here is to understand that we only consider the charge inside the closed surface. Now, there are several conditions for using Gauss's law. Before we get to that, look at this question. What is the electric flux through a spherical surface of radius zero point 0.5 meter surrounding a charge of 2 times 10 to the negative 9 coulomb? You're given the radius, you're given the charge. According to Gauss's law, the electric flux is Q by epsilon naught. So Q divided by epsilon naught. You notice that the radius given has not been used because it doesn't matter. The reason being, if you have a charge, and let's say that you consider a surface around it, and then you consider another surface around it, the electric flux passing through both of these surfaces is the same. Because whatever is the electric flux passing through surface A must be the flux passing through surface B. Because when you consider all the field lines, everything that passes through A also passes through B. I hope that is clear enough. Now, here's the second one. A cube encloses multiple charges and the total is given as 10 to the negative 6 coulomb, what is the net electric flux through its surface? Once again, there is no mention of the size of the cube here because it does not matter. All you got to do is cube by epsilon naught, and you get the answer. And this diagram, in fact, try to illustrate the flux or the field lines that's perpendicular to the surface uh, in the xy plane. So if you were to consider this, you would get the flux as E naught, let me write that, E naught times A times B. Why? Because that's the area. So the electric flux would be E naught times A times B times cosine of what? 0 degrees. Once again, remember that the angle is taken perpendicular to the surface, so that's why it's cosine 0, which is 1. So the answer is E naught AB. That's what is shown there. Now, this diagram shows several charges that are inside and outside. But if you were to consider the flux passing through this shaded surface, then you would only consider the charges Q1, Q2, and Q5. Also, when you consider the charges, since one of them or two of them are negative, you'll have to go be careful and say, okay, flux through this is 1 by epsilon naught times Q1 minus Q2 minus Q5. So if it's a positive charge, you put a positive. If it's negative, you put a negative. So that's how you take the sum. So that's another thing that you have to be careful about. Okay. So let's talk about the validity of Gauss's law. Gauss's law is valid universally, but it's only practically useful for calculating electric fields when the system exhibits certain types of symmetry. I'm going to explain that. Now, this is because this ensures that the surface integral simplifies and allows us to solve for E algebraically. Now, when you talk about the symmetries, these include spherical, cylindrical, and planar symmetry. Without symmetry, the math becomes too complex to apply Gauss's law effectively, and you're going to see that. So, here are some conditions of high symmetry. The charge distribution must exhibit one of the following. Spherical symmetry is when you have a point charge. That means an isolated charge situated somewhere, just like that. Or you have a sphere that's uniformly charged. Cylindrical symmetry is in the case of a long charged wire. And planar symmetry is in the case of an infinite sheet of charge. Now, among the conditions for practical use, we also understand that the electric field must either be constant in magnitude and direction over the parts of the surface, or it must be zero. And also, the angle between electric field and the area must be constant, or it should be easily defined. Number three, when you try to calculate the flux, you always imagine a surface. Okay, so you have an isolated charge and you imagine a surface. This surface is called the Gaussian surface. And the Gaussian surface should conform to the symmetry of the problem. And this is when it allows easy evaluation of the integral. We're going to use this and then it'll become more clear. Right now, it's just like what's going on. All right, let's apply this. A uniformly charged sphere of radius r has a total charge q. Can Gauss law be used to find the electric field? In this case, at a point outside the sphere? The answer is yes, because the system has spherical symmetry. And how would we use it there? Remember that on the left side, we had for flux, let me write that for flux, what we have is integral, closed surface integral, E dot dA, right? Now, when electric field is a constant, that can be taken out. So now you have E dot closed surface integral dA. Now, when you talk about closed surface integral dA, you're talking about the area of the surface, or in other words, surface area. And that's where you get 4 pi r squared. Because 4 pi r squared is the area of a surface. I hope that's clear. So the electric flux is E times 4 pi r squared is equal to Q by epsilon naught. And on rearranging, you get E is Q by 4 pi epsilon naught r squared, which gives you the electric field at a distance r from the sphere. So if you have that sphere here, and that's a center, and you want to find the electric field at that point, this is the distance r. So the charges are actually on the sphere. Let's say it's positively charged. But when you take the distance, you take it from the center of the sphere. There's a second example where Gauss's law cannot be applied. A cube encloses a non-uniform charge distribution. Look at that. Can Gauss's law be used in this case? No, because a cube lacks symmetry, and Gauss's law is valid in every case, but not useful in this case, okay? Because it's a non-uniform charge distribution. Now, I'm not going to take much time on this problem because it's exactly similar to the previous one, except that the numbers are given here. So we have a uniformly charged spherical shell radius given, carrying a charge. Find the electric field at a distance, small r, zero 0.5 meter from the center. Now, what is to be noted is that the radius of the sphere is immaterial here. We don't care about that because we only care about the radius of the Gaussian surface. And if you want to find the electric field at a distance 0.5 meter from the center, then that's where we imagine the Gaussian surface passing through. So that's why you only have little r. And then from the last question, you understand this is what we get. When you plug in the numbers, you get the value. All right, here's the second one. It's on an infinite plane sheet of charge. The surface charge density is given. You may remember from the previous chapter that that is charge divided by total area, or the charge on 1 meter square. Find the electric field just above the surface. Okay, here there is planar symmetry. Well, in the last case, it was spherical symmetry because it's a plane here, and you have to use a pillbox-shaped Gaussian surface perpendicular to the plane. I'm going to try to draw that quickly and try to show you. Okay. So if you have that plane surface like that, the pillbox type surface you're trying to imagine is going to be a cylinder actually passing through the surface. See that? That's what you're trying to consider. We're going to use this and derive it, but for now, consider the formula E is equal to sigma by 2 epsilon naught. This is the formula for electric field due to a single infinite plane sheet of charge. And it's very important in the next chapters, this formula. Now, in this case, sigma is given, and 2 times epsilon naught, and you get the number 1.69 times 10 to the 5 Newton per coulomb. Okay, so I think we had discussed all this, and this is just some diagram showing you that there is cylindrical symmetry there. But here, because the charges are of different densities, look, here the charge density was the same, but here you have two different, so it's not symmetric. Again, it's not symmetric here. But in this case, you can see that although the charge density is changing, it's changing in a regular manner. So therefore, it's still cylindrically symmetric. Okay. So the idea is to find the electric field at any point. What you have to first do is, okay, let's say there's a charge there, and you want to find the electric field at this point P. You have to imagine that there is a Gaussian surface passing through that point. And then you have to apply Gauss's law, which is what we have done. So if it's a spherical symmetry, as I have shown, then all that matters is this distance r from the charge, see? And you would end up with this formula. Now, now, if the charges are, okay, let me take this out. And if the charges are on the sphere, so let's say it's a sphere, and this is charged, uniformly charged, although I'm not drawing everything. And you want to find the electric field at this point, P. Okay. So now what you have to do is you have to imagine a Gaussian surface passing through that point, right? Now, how many charges do you have inside that Gaussian surface? Nothing. That means there is no electric field inside a charged sphere, inside a conducting shell. Okay? Because you know that according to Gauss's law, E dot dA is the enclosed charge divided by epsilon naught. When this becomes zero, that means E dot dA is zero. Now, the area cannot be zero, which means that the electric field is zero. Now, this is a very important concept that if you charge a shell, you have a conducting shell that is charged, you are safe inside that shell because there's no electric field inside a charged conductor. And then if it's cylindrical symmetry, you have to know this formula. E is lambda over 2 pi epsilon naught r. This is the case where you have a long wire like that, which is charged. And lambda is the charge per unit length. Remember this from the previous chapter. So if you have the total charge on that long conductor and you have its length, you get lambda because lambda is the charge density per unit length, okay? So in this case, the formula is lambda by 2 by epsilon naught r, which I have not derived, but you have to know the formula. And once again, for an infinite sheet, it's sigma by 2 epsilon naught. So four cases: outside a sphere, inside a sphere, um, for an infinite line of charge, and for an infinite sheet. Remember, it's both valid only if they are infinitely long, that extending. Okay. Now, this is just to illustrate again. At electrostatic equilibrium, the electric field inside a conductor is zero, but outside you have the electric field. Now, this could be a short question. So, why is the electric field zero again? We know we got it by applying Gauss's law, but practically we can explain it saying conductors contain free electrons and therefore they move in response to electric field. They are movable. If there was a non-zero field inside, charges would continuously move, which means the equilibrium is lost. Look at that. So when we say that charges are on a sphere, that means the charge is not moving, so it's in perfect equilibrium. Therefore, it's also to be understood that charges always rearrange themselves until the internal electric field cancels completely. Charges just redistribute in such a way that there is no electric field inside a charged conductor. Consequences? All excess charge resides on the surface of a conductor. Important. So even if it's a solid conductor, like a copper ball, you charge it, where are you going to find the charges? Only on the outside, because all of the charges will move slowly and situate themselves on the surface of the conductor. And that means its interior is shielded from external fields. Any cavity within a conductor has no field inside it, because if it has no charge. If it has a charge, then there will be. All right, a solid copper sphere, see that, is placed in an external electric field. What is the electric field at the center of the sphere once equilibrium is reached? Zero. You take that sphere and keep it in an electric field, still no field will pass through its inside. Also, at electrostatic equilibrium, the electric field just outside is perpendicular to the surface. Look at this. These are perpendicular to the surface. Now we talk about the field outside. And it has a magnitude directly proportional to the surface charge density. We know that because that's the formula. So if sigma is big, then E is big too. All right, why should it be perpendicular? Because if it has a tangential component, then the surface charges would move once again. So if that's the surface and you have a component that way, the charges here have to move, which means equilibrium is lost. But as long as it's perpendicular, it has no effect on the charge because the y component is not affected by the x. That's why field lines are always perpendicular to the surface. So here are some questions that are a repeat. A conductor has an electric field at an angle of 30 degrees to the surface. See, there's something wrong there. Is the conductor uh, electrostatic equilibrium? The answer is no. Why? It cannot be at 30. It has to be perpendicular. A metal sphere contains an electric field of 120 Newton per coulomb inside it. What? Inside. Is this possible? No, because we know that the field inside is zero. If there is a field, that means equilibrium has not been reached. That is what it shows. That's what it represents. So that is basically this chapter. So you have to understand the concepts here. So in conclusion, Gauss Law connects electric fields and charge distributions in a profound and practical way. By recognizing symmetry and understanding field behavior in conductors, we gain powerful tools for analyzing electrostatic systems, as we're going to see in the chapters ahead. I hope all of this makes sense, and it'll make more sense when we apply it, especially in the case of capacitors. Thank you. We'll see you on the next one.